Hi, hello everybody. In today's class, we'll see what graph theory is, we'll define what a graph is, we'll see various kinds of graphs that are possible, and we'll see properties of graphs, and we will see some of the applications of graphs. The graph applications are really immense. Most of the practical problems, be it in computer science or be it any other discipline, can be modeled as computer science and can be studied very nicely. That problem can be studied very nicely. So, we'll see what a graph is, general meaning of the graph, that is, in mathematics we'll write this as a graph. This is what we mean here by graph. It's not a plot or chart of numerical data using coordinate system. The technical meaning of a graph in discrete maths is it's actually a discrete structure that is very much useful for representing a relation. Relations we have seen, isn't it? If you have got a set A, you can talk a binary relation on set A like R is subset of A cross A. Any subset of the Cartesian product A cross A will be a relation. Actually, graph is a nice way of representing this binary relation, and the advantage that it will have is it will have a nice webby looking graphical representation. A graph is typically represented like this. You can nicely represent it in the form of nodes and edges. Let us see it now. And as far as the application go, it has got immense applications, and be it networking, be it scheduling, be it an optimization and circuit design, path planning, and anywhere you go, it has got a lot of applications. The problem can be nicely modeled as graphs and can be studied thereupon. And basically, let us define simple graph. A simple graph basically corresponds to a symmetric irreflexive binary relation. What I mean by this is, let us go back and see what a symmetric irreflexive relation. If V is a set, then I can define a relation on V like this. Any subset of V cross V, any subset of the Cartesian product is a relation, and if this relation we say symmetric when if A comma B is in R, then B comma A is also in R, then we say this relation a symmetric relation, otherwise not. And irreflexive means you take any A in V, you take any A in V, then A comma A should not be there in this relation. Then we call the relation R is reflexive. Basically, let us see now how this particular irreflexive symmetric relation can be nicely represented as graph. A graph will have nodes as the elements of the set V that we considered. All these guys are nothing but the elements of the set V on which we spoke the relation. All these guys are called nodes or vertices in graph theory. Basically, these are the elements of the set V, and whenever in this relation there is a guy, there is an element in this particular relation, say U comma W is an element in this particular relation, correspondingly U will be definitely a vertex and W will be another vertex, isn't it? Then correspondingly there will be an edge between this U and W vertices, that is called an edge. So the set of edges are nothing but unordered pair of elements U comma V such that U and V are in the relation R. Okay. So what I am saying here is, if you are having a set V represent and a binary relation on the set V, represent all the elements in the V by nodes and connect them if the corresponding tuple is there in this particular relation, otherwise not. The corresponding diagram that we get is called a graph, and obviously this is corresponding to the symmetric irreflexive relation that we are speaking on the set V, that is a set of vertices. Let us take an example of the set V, which is representing set of all states in far southeastern US. These are all the elements of the set V. So I will represent all of these by these particular nodes. Then the relation that I am speaking here is the two guys, say for example FL comma GA is going to be there in my relation if they are neighbors, otherwise not. Then I will definitely get a symmetric relation. And to represent it as a graph, what we will do is, you represent all these guys by nodes like this: LA, MS, AL, TN, NC, SC, GA and FL, and whenever they are neighbors, put a line or straight line, put a line between them, which we call a edge. All the states we are going to call them as nodes. The resultant graph looks like this, wherein each node is a state, and if they are neighbors, they are connected by a line. And you take a simple graph. Generally, simple graph will have only one edge between two vertices, isn't it? That is how it is defined. But we will define, and in a particular kind of graph called multi-graph, you will not be restricted by this condition. That means between any two nodes you may have more than edge. You may have two edges between two vertices, or you may have 3, or you may have 4, or you may have 5. You can have as many number of edges between two vertices. That is very much okay. But this kind of graph is called a multi-graph. Okay. And in a simple graph, we don't have edges running between the same vertex. What I mean is, when we call this a graph, always we mean an edge is between two vertices, isn't it? Two vertices, because a simple graph is nothing but irreflexive symmetric relation. In irreflexive, you cannot have A comma A belonging to that particular relation, isn't it? If A comma A is not in R, then we call R a irreflexive relation. Hence, since simple graph is representing an irreflexive relation, A comma A, that is an edge connecting a vertex with itself, is not going to be there. But we relax this particular condition and we get another kind of graph that is called pseudo graph, wherein you can have an edge from a vertex to itself. That is called a loop. This is called a loop, and this graph is called a pseudo graph. For example, this guy, this is a loop, isn't it? This is a loop, isn't it? And in fact, this is a multi-graph because between these two vertices you have got more than one edge. Hence, this thing, this structure is called, this graph is called a pseudo graph. we have been saying a simple a symmetric irreflexive relation corresponds to a simple graph, but if we drop the symmetric condition, then the corresponding graph is called directed graph. It is as simple as from one node to another node. When you are saying we put a direction to it, this particular edge is going from where to where. Here this particular edge is going from this particular vertex to this particular vertex. There is a direction to it. And simply saying, because you got a direction like this, when u comma v is in R and it is not symmetric, it is asymmetric, then if it is not symmetric, then you really don't know whether v comma u is there in this particular relation. You don't know really. It can be there, it need not be there, because we have dropped the property of symmetricity from the relation. The resultant graph will be a directed graph, in which when you are said that there is an edge called u comma v, you really don't know whether the edge called v comma u is there in the particular relation or not. There is a direction associated to it. In a directed graph, you say that an edge is running from this vertex to this vertex. If you, for example, we can take, you consider the set of all human beings, and I say plot them like this, all the guys as vertices, and I say that I will put a vertex, I will put an edge from this guy to this guy. If u loves v, then I put this particular edge, otherwise I am not going to put that particular edge. Or equivalently saying that the tuple u comma v is going to be there in the relation if u loves v, otherwise not. If that is the relation that I am defining, you will get nice a graph, isn't it? This is going to be directed because u loves v doesn't mean that v is loving u. It is not symmetric basically. So there is a direction whether u is loving v or v is loving u. When you are to say kind of these things, then you get into directed graph modeling. Basically, when you would like to represent a relation which is not symmetric, then you can represent that relation probably by directed graph. Unlike a directed graph, when I say directed graph, simply the directed graph may not have edges, may not have more than one edge running from one vertex to the another vertex. This condition has been relaxed. That means a directed graph may have more than one edge running from one vertex to the other vertex. When we relax this particular condition, what we get is directed multigraphs. Look at this guy. This guy is having between this vertex and this vertex more than one edge running out. Hence, this structure is called a directed multigraph. And the best example for this is, you take set of all web pages and edge set as you link two web pages. If there is a link from one web page to the another web page, you put this kind of relation, then the corresponding relation is represented as a directed multigraph, isn't it? You take two web pages, if they are related, if one web page is calling another web page, you put a directed link like this, otherwise not. So now you consider all the web pages. All web pages turn out to be vertices, and if one web page is calling another web page, put a directed edge. The resultant graph is definitely a directed multigraph. It is multi because from one page you may be calling another page a number of times, isn't it? There will be several hyperlinks from one web page to the another web page. So it is multi-graph, and it is of course directed. That's a typical example of multi-graph, directed multi-graph. And if you consolidate what we have studied now, simple graph is nothing but it is basically undirected because it is representing a symmetric relation, and there are no multiple edges because it is irreflexive, and we don't have self loops inside a simple graph. This is what simple graph is. If you go back to multi-graph, we will relax this particular condition of whether there should be multiple edges or not. We will have multiple edges inside a multi-graph. That is what the condition we relaxed. And in pseudo graph, we relax the condition that it can have self loops. That means there can be an edge that is running from the vertex to itself. And you can have directed graph, means basically it is representing a relation which is not symmetric, equivalently saying we are talking a direction from one vertex to the other vertex. A directed self loop graph is called a directed graph, and a directed self loop and having self loops and having multiple edges is called directed multigraphs. And depending on the situation, depending on the problem that you are dealing, you have to model it as the corresponding graph. Okay, and now let us understand some terminology that will be used in graph theory. Terminology like what is adjacent, what is connects, what is degree, and what is bipartite, and what is a cycle, what is a wheel, and all these things. Say we have got a undirected graph like this, and we all know this guy is an edge, this guy is an edge, this guy is an edge, this guy is an edge. There are lots of edges over here. I'll take an edge like this particular edge I'll consider. This edge is typically called the pair A comma B, isn't it? This edge is denoted by this pair A comma B. Then what we say is A and B are adjacent. It's quite meaningful, isn't it? When I have got an edge between A and B, then I say A and B are adjacent, or A and B are neighbors, or A and B are connected. All these things are equivalent. It only says that there is an edge between A and B, or equivalently A comma B is there in the corresponding relation. Then we say that A and B are connected. And we can also say that if we call this particular edge by edge E, if we say that this is the edge E, and then we say that this edge E is incident with the vertices A and B, isn't it? Because this is the edge that I am speaking, I am denoting this edge by E, and I say this edge is incident with two vertices, that is A and B. Or equivalently we can say that A and B are end points of the edge E. Okay, if somebody comes to me and says that, sir, I have got a graph in which E is the edge and it is connecting two vertices X and Y, then I can say, I can infer a lot of things. X and Y are adjacent vertices, and E connects the vertices X and Y. Like these things I can infer. Say we have got a graph like this. Let us define what is the degree of a vertex in a graph. Suppose this is a simple directed graph. The degree is nothing but how many edges are incident with A, or how many edges are going from the vertex A. How many edges are incident, how many edges are incident edges for this vertex A? 3, this is 1, this is 2, this is 3, isn't it? So degree of A is known as 3. We will come here. What is the degree of C? Degree of C is 2 because there are 2 edges that are incident with it. Degree of E is 3 because there are 3 edges that are incident with it. And just for terminology, we say that a vertex with degree 0 is an isolated vertex. You want to see an isolated vertex? Suppose I consider this particular graph. Is this a graph or not? All this together, it's very much a graph. Don't think that because there are no edges between this vertex and any of these vertex or any of these vertex, this cannot afford to be not a graph. This is very much a graph. And what is the degree of this? Degree of this is 2, degree of this is 3, degree of this is 2, degree of this is 1, degree of this is 0, because no edge is incident with this particular vertex. Hence its degree is 0. This vertex is called an isolated vertex. Obviously, isn't it? This is isolated. It is not connected to anybody. Hence it is called an isolated vertex. And we will see what is the degree of this particular vertex. The degree of this particular vertex is 1. Degree of this particular vertex is 1, and this vertex is called pendant vertex. That is just terminology. Both meanings are very much, both words are very much meaningful, isn't it? If a vertex is not connected to anybody, it is called an isolated vertex, and if it is connected to only one vertex, it is called a pendant vertex. Now let us see a nice theorem about the degree sequence or degrees of vertices of a graph. It says that let G be an undirected, it can be simple or it can be multi or it can be pseudo graph with vertex at V and edges at E. Then if you sum up all the degrees of all of its vertices, if you sum up degrees of all vertices of that particular graph, then that is nothing but twice the number of edges inside that particular graph. If you got a graph like this, if this is the graph, then what it says is that what is the degree of sum of degree of all vertices? What is the degree of this guy? 1, 2, 3, 4. 4 plus 3 plus 3 plus 3 plus 3. You just sum up all degrees, then it is going to be the twice the number of edges inside that graph. How can we prove it? if you carefully observe each edge, if you take this particular edge, it contributes 2 to the sum of degrees of vertices, sum of degrees of vertices, isn't it? If you take this particular edge, it contributes 2. Why 2? It has been one for this degree and another for this degree, isn't it? It actually, you take any particular edge, it contributes 2 to sum of the degrees of vertices, because an edge is incident with exactly 2 vertices, isn't it? So because each edge is contributing 2, how many edges are there? Actually, cardinality of how many ever number of edges are there, twice that number is being contributed to the sum of degrees of all vertices. Hence, this equality holds good. It's very simple to understand. Observe the simple fact that each edge contributes 2 to the sum of degrees of vertices. Then how many edges are there? What the cardinality of edges are there? Then how much all the edges together contribute to? 2 mod it contributes to. It is contributing to whom? The sum of degrees of all vertices. Hence, this particular equality holds good. So, we will prove the corollary to this particular theorem, that is, any undirected graph has an even number of vertices of odd degree. What it means is, if you have got any graph, if you have got any graph like this and you find out how many vertices are having odd degree, it may have 1, 2, 3, 4, 5, maximum 5, because there are only 5 vertices are there. The number of vertices which are having odd degree, what this corollary is saying is, such number can be only even, it cannot be odd. So, the number of vertices of odd degree can be either 1 or 3 or 5 in this example. It cannot be 2 or 4. Sorry, it can be only 2 or 4, but not 1, 3 or 5. The number of vertices of odd degree can be either 2 or 4. It cannot be 1 or 3 or 5. That is what this particular corollary is telling us. Let us try to prove this corollary. I will say that I will just get this notation. V1 is set of all vertices of even degree and I define V2 is set of all odd degree. Then I can obviously say that V is nothing but union of V1 and V2, that I can say. Then I just apply handshake theorem here. What is the handshake theorem saying us? That twice the number of edges, I say E is the number of edges, total number of edges in this particular graph. Then I can say that 2E is equal to sigma of degree U. That means sum of all sum of degrees of all vertices. But if you carefully observe, because V is a disjoint union of V1 and V2, you can in fact write like this: set of all vertices that are there in V1 plus the degree of all vertices that are there in V2. This is but obvious, because V happens to be the disjoint union of V1 and V2. And now if you carefully observe, V1 is the set of all vertices of even degree. That means you take any member in V1, its degree is an even number, that is, it is either 0 or 2 or 4 or 6 or 8, an even number. So all the vertices in V1 are going to have even numbers. So when you add all of them up, then this is definitely an even number. Is there any doubt about it? Because each member inside V1 is having degree as even number. Degree of that particular member is an even number. When you add all these degrees, then the resultant number is an even number, isn't it? Now what we need to prove is the number of vertices in V2, basically the number of vertices in V2, that is the number of vertices of odd degree or even, that is what we need to prove now. The number of guys in V2 is even, that is what we need to prove. Suppose not, I will prove this by contradiction. Suppose not, what does it mean? The number of guys in V2 is odd. That means V2 is having odd number of vertices, and each vertex is having degree as an odd number, isn't it? Degree of each vertex is odd. So if you add all these degrees, each degree of each vertex is odd, and so you are adding odd number of times, because the number of vertices in V2 is odd. The number of vertices in V2 is odd, and each guy is having its degree as an odd number. So when you sum it up, it is going to be definitely an odd number. So finally what we got is an even number. When you got 2e, that is definitely an even number. An even number is sum of an even number and sum of odd number, which is very much a contradiction. These sum up to an odd integer, these sum up to an odd integer, and this is an even integer. This is a contradiction, isn't it? This contradiction has been arised due to the fact that we have assumed the number of vertices in V2 is odd. Hence it is not correct. Hence the number of vertices in V2 is even. Number of vertices in V2 is even means the number of vertices having odd degree are even. That is how we proved this theorem. I hope this is very clear. 2e summing up to degrees of vertices in V1 plus sum of degrees of vertices in V2. Till here this is no problem, and this being an even is no problem, because degree in V1 is an even number, and whether we have got how many ever number of guys there in V1, their sum is always going to be an even number. The problem is with this guy, we have to prove that the number of guys in V2 is even. That is what we need to prove. Here I am applying contradiction. I say that no, there are odd number of guys in V2. When I say odd number of guys in V2 and each guy is contributing an odd number, when I sum all of them up, when I sum all the degrees up, I will get an odd number. So resultantly I get an even number and an odd number here which contributes to an odd number, but actually this is equal to an even number, which is a contradiction. This is what proof by contradiction. Hence what our assumption should be wrong. What is our assumption, that what is the thing that we started with? We thought that the number of guys in V2 is odd. That is wrong. Hence number of guys in V2 is even. That is how we prove this particular corollary. And just in the same way that we proved adjacency in undirected case, when you got a directed graph like this, when we have got a directed graph like this, and when we know A, B is an edge in this particular graph, then when the direction is from A to B, then we say the edge E, say we are representing this particular edge by E, then we say E comes from A to B, or equivalently we can say that E connects A to B, or we can say that initial vertex of A is initial vertex of E is A and the terminal vertex of E is B. All these things are equivalent. We can say A is adjacent to B when we have got an edge that is E working, that E emanating from A to B. In this kind of situation we can say that A is adjacent to V, or V is adjacent from, or B is adjacent from A. All these things we can say. And in case of directed graph, we can talk the degrees also the same way we spoke in undirected case, in an undirected graph. Suppose this is the directed graph. This is the directed graph. If this is the directed graph, here more than just a degree, we speak of in degree and out degree of a vertex. The out degree of this particular vertex is defined as how many edges are going from it. In this particular example, how many edges are going from it? Are going, or how many edges are emanating from this particular vertex V? Two edges are coming from V. Two edges are coming from V, isn't it? Or emanating from V, isn't it? So we say out degree of this V, vertex V, is 2, and this is called out degree. In this particular example, out degree of V is 2 because 2 edges are going out of it. And we say in degree of vertex V, how many edges are coming into V? How many edges are coming? In this case, one edge is coming into V. Hence in degree of this particular vertex is 1. However, we define the degree also. It is the sum of out degree and in degree. In this case it is 3. That is how the in degree out degree is defined for a directed graph. And if we have got a directed graph with vertex and the same handshaking lemma what we have spoken for undirected graph, we can speak for directed graph also. If you carefully see it and applying the same principle that each edge in undirected graph contributes 2 to the sum of degrees of all vertices, applying the same principle with in degree out degree, we will get this particular equality. If you have got a directed vertex, directed edge, it contributes respectively to the sum of in degree or out degree. So using the same technique we can prove even this particular equality. And now we will see some special kinds of graphs. A complete graph, cycle, wheel, cube, bipartite graph and complete bipartite graph. A complete graph is nothing but when you got, say, the vertex set happens to be having n vertices, then typically the graph that you can speak on this particular vertex set may not have all possible edges. How many possible edges are possible on n vertices? Actually n choose 2 possible what edges are possible, isn't it? A graph can have anywhere between 0 to n choose 2 vertices, n choose 2 edges. Any combination, any tuple of this vertex set is an edge. So how many tuples, how many pairs are there? Are there any pair of vertices is an edge, isn't it? That is how actually an edge has been defined. Any pair of vertices. How many pairs are possible? N choose 2 pairs are possible. So n choose 2 edges are possible. So when you talk a graph on n vertices, a graph can have the number of edges anywhere in between 0 and n choose 2. Anything is possible. It may not have any edges between them like this. Is this a graph or not? This is very much a graph. In fact, this is a graph where each vertex is an isolated vertex. So this is a graph with 0 edges, and similarly you can have a graph with all possible edges. What does it mean? All possible edges means every guy is pairing up with all other guys. Every node is pairing up with all other nodes, or every vertex is adjacent with any other vertex. Such a resultant graph is called complete graph. It is complete because no edge is left out. In this case, the complete graph looks like this. Because it has to be connected to each guy, I will connect like this, and this guy need to be connected to everybody, I connect like this. This is a complete graph. Every vertex is connected to all other vertices. It has got the special notion that if n is the number of vertices, we represent the complete graph by kn. Let us see how does k1 looks like. K1 means there is only one vertex, so there cannot be any edge. Because it is basically complete graph is only talked for simple graphs. we say complete graph means it is complete simple graph basically. Because it is a simple graph, it cannot have any loops. Hence, if you say that there is only one guy with me, you cannot afford to have any edge inside that particular graph. So this is called K1. This is a complete graph. What is K2? This is called K2. Why? There are two vertices and between these two vertices there is an edge. That's it. You got all vertices connected to other vertices. Only two vertices, they are connected. Hence, this is a complete graph. This is called K2. What is K3? You got three vertices. All of them are connected. This is K4. You got four vertices. All of them are connected. See, this guy is connected to everybody. 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 And this is K5 and K6. That is how you can do it. And if you carefully observe how many number of edges are there in a complete graph, it is going to be n into n minus 1 by 2. So this is very simple thing to prove. We again use our handshaking lemma here. What does handshaking lemma says? Twice the number of edges is equivalent to degree of all vertices. That is what our handshake lemma says, isn't it? Now look at a complete graph. Look at the complete graph. For example, this guy K5, you look at it. What is the degree of vertex of this particular vertex? It is going to be 1, 2, 3, 4, isn't it? Why it is so? Because this guy is connected with the rest of vertices. How many guys are there? N minus 1 guys are there with whom he is connected. So what is the degree of this guy? Degree of this guy is n minus 1. In this case it happens to be 4. What is the degree of this guy? 4, that is n minus 1. Degree of this guy n minus 1. So each guy is having degree as n minus 1 in case of a complete graph. And so it is going to be sigma u belong to V n minus 1. Okay, how many guys are there in the vertex at V? Because we are talking for Kn, n vertices are going to be there in the graph. Hence, so there are n of them are there. So the sum is nothing but n into n minus 1, which obviously says that the number of edges is n into n minus 1 by 2. I mean, E is the number of edges. That is how we started. If E is the number of edges, because of handshake lemma we have got this particular thing, and in complete graph degree of each vertex is n minus 1, hence we have got this. But there are n vertices inside the vertex at V, inside the complete graph, hence we have got this. And when we do simple arithmetic, we will get that E is n into n minus 1 by 2. That means to say that the number of edges inside a complete graph is n into n minus 1 by 2. And when we have got a vertex set like V1, V2, Vn, and then if it is a simple graph, and if V1, V2, V2, V3, Vn minus 1, Vn, Vn, V1, if there are edges between all of these guys and there are no more edges, we call the corresponding graph is a cycle, and it's quite useful. In this case, see, from say 1, 2, 3, there is an edge from 1 to 2, 2 to 3, and 3 to 1. This is called a cycle. Edge from here to here, here to here, here to here, here to here, this is called a cycle. This is called a cycle. And because there are 5 vertices, I call this a cycle 5. This is C4, this is C3 and C6. And if you ask me how many number of edges are there in Cn, it is but obvious. It's n, because it's a cycle. You start from here, go here, go here. How many times you are traversing, how many edges are there? It is n. This structure is defined like, cycle is defined like this. If you have got a vertices, then it should be looking like a cycle when you nicely join them with edges. We will see what a wheel is. Any graph which assumes this particular structure is called a wheel. It is wheel like a typical wheel of a cycle or a motorbike. Should have a guy in between, and the other thing is cycle, and this guy is connected to everybody else. This is called a wheel, and in this kind of structure we call this hub, and all other guys are called vertices, and this hub is definitely connected to everybody else, and all others form a nice cycle. The resultant structure is called the wheel. And how many number of edges are there in wheel n? Because basically here the answer varies when you consider the vertex V hub as part of the vertex, you will get some answer, and if you exclude it from the vertex set, then you get different answer. Basically the number of edges are nothing but sum of all these things plus these guys, isn't it? That's it, as simple as that. Now let us look at another kind of graph. This is called a hypercube. The hypercube is, this is where again we will prove something by recursively we prove this hypercube. I have been saying how you can define a function recursively, a set recursively. That is what we have seen in the last before class, in the recursion class. Here you can see how a structure can be defined recursively. It has been defined like this. If you have got two cubes, say qn minus 1 and qn minus 1, you take these two cubes and you connect the corresponding vertices in qn minus 1, the resultant structure is called hypercube qn. We will see how it is. Okay. So we will say we will take two cubes, q naughts we will take. What is q naught? Q naught is nothing but a vertex, no edge there at all. If you take two q naughts, it will be like this, isn't it? This is one q naught, this is another q naught. What I mean by connecting corresponding edges means this is an edge and this is an edge in another cube. Connect them, what you get is q1. Okay, and say you have got two q1s, this is one q1 and this is one q1. Okay, what I mean by correspond, this and these are corresponding vertices. There is a one-to-one mapping between these guys, this and this, isn't it? Connect them, then you get q2, isn't it? Because there is one-to-one correspondence between the vertex here and this and this. That is the function. Connect them, you get q2 out of it. Say you have got two q2s. How do they look like? They look like this. You got two q2s. Here what I mean by corresponding vertex is this corresponds to this particular vertex and this corresponds to this particular vertex, this corresponds to this guy, this corresponds to this guy. It's just about symmetricity, isn't it? So when you how q3 is defined, you know, you take two q2s, this is one q2, this is one q2, and put an edge between the corresponding vertices. And this is q3. This is what q3 is. You take two q2s and q3 you will get like this. You take two q2s and connect them, connect the corresponding vertices by edges. What you get out is q3. That is how we define a structure recursively, isn't it? If I know the structure of the lower orders, that is q2 in this case, then I can define what q3 is. I take two q2s and I don't do anything, I just connect the corresponding vertices. The resultant structure is called q3. And if you carefully observe how many number of edges are going to be there in q3, it is very obvious, isn't it? The number of edges in q2 plus the number of edges in this q2 plus the number of edges that I am adding. How many edges that I am adding for each vertex in this particular q2? I am adding one edge, that's it. How many edges are there in this q2? There are 4 edges. So the number of edges that are going to be there in q3 is nothing but the number of edges in q2 plus number of edges in q2 plus the number of vertices in q2, because each vertex will give me an edge in the new structure, that is q3. It is like this, isn't it? That is what I told. This is q3. Okay. Now let us find out how many number of edges are going to be there in qn, that is n into 2 power n minus 1. Let us prove it. Again we will prove it by induction. Suppose we will prove the theorem. We will suppose the theorem is true for qk, then we are going to prove the theorem is for qk plus 1. Qk implies qk plus 1. This is what I am doing in my induction step here. What does it mean by qk is true for theorem is true for qk? That means that the number of edges in qk are k into 2 power k minus 1, because this is what we need to prove. I mean qn, we have to prove that n into 2 power n minus 1. When I say that the theorem holds good for k, that means that number of edges in qk are k into 2 power k minus 1. And we know that the number of edges that are going to be there in qk plus 1 are nothing but the number of edges in qk and the number of edges in another qk and the number of vertices in qk. That is what we have seen. That is how we actually, these guys are connected. In this case, how did you get q3? You take two q2s and you connect the corresponding vertices. So the number of edges in q3 is nothing but number of edges in q2 plus number of edges in q2 plus number of vertices in q2. In the same way, so by induction we know, by induction hypothesis we know the number of edges in ek as k into 2 power k minus 1, this as k into 2 power k minus 1, and how many number of vertices are there in qk? But obvious 2 power k, because how it is defined. The q0 is having one vertex, q1 is having two vertices, q2 is having 2 square vertices, that is 4 vertices, qk is going to have 2 power k vertices. So many edges are going to be there in finally in your qk plus 1. So just add them up, do some basic algebra, you will get finally the number of edges in qk plus 1 is k plus 1 into 2 power k. Another kind of interesting graph is, if you can have the graph that has been divided into two vertex sets, say V1 and V2, these are all vertex sets, then if you have got all your edges inside the graph in such a way that every edge is from a vertex in V1 to vertex in V2 and there are no edges that are connecting two vertices in V1 or two vertices in V2, when you have got such a kind of graph, then you say it is a bipartite graph. Basically it is called bipartite because you have got two partitions of vertex sets V1 and V2 and all your edges are connecting only these two vertex sets. The graph can be divided into two parts in such a way that all edges go between these two parts. It is called a bipartite graph, and a complete bipartite graph is nothing but, say you got one partition, another partition, say this is having M and this is having n vertices. If you got an edge from this vertex to all other vertices here, and this is holding good for all vertices in this partition, then we say it is a complete bipartite graph. That means each vertex here is connected to all vertices in another partition, and definitely it is represented as KMN if this partition is having m vertices and if this partition is having n vertices. Then how many nodes that it is going to have? It is definitely going to have m plus n nodes. And how many edges it will have? It will have mn edges, because each guy here is resulting is giving us n edges. There are m guys there, so the number of edges are going to be mn. Okay, in today's class what we have seen is what a graph is and how actually it is representing a relation in a very webby looking way. And we have seen the basic terminology that is being used in graphs. What is an edge, what is adjacent, what is neighbor, when do you say two vertices are neighbors, and what is the degree of a vertex. And we have seen handshaking lemma that relates degree of vertices to the number of edges in the graph. And we have seen some special kinds of graphs like cycle, wheel, cube and bipartite graph. Thanks for today's class, and let us meet in the next class again. Bye.